So far we have dealt with combined uncertainties when they came from the same distribution. So for example, we had our 3 bananas that we measured, and here are the measurements for the bananas, and we could calculate the sample uncertainty. But we also know that we have another uncertainty here, which comes from the resolution of the kitchen scales. And we have done that in one of the previous videos, where we said the resolution of the kitchen scale, so resolution is 1 gram, and therefore we can say we don't know where the actual exact value is, so we would use a uniform distribution, and I showed you that the uncertainty for a uniform distribution is given as resolution divided by 2 times 1 over square root 3. So if our resolution is 1 gram, we would get here an uncertainty of 0.288 gram. And this is something that we can do even without any kind of measurements. We don't need to do any measurements. This is an uncertainty that we can just derive from the equipment that we use, and this is called a type A uncertainty, because it is just simply derived from the equipment. So we can actually say the uncertainty for our bananas would be 99 gram plus minus 0.288 gram for each measurement, plus minus 0.288 gram plus minus 0.288 grams. Because every measurement has this issue here. And now we've got also a sample here where we said we can calculate the sample uncertainty for that. And I showed you how we do that. So we can do that by taking the average, that's the x bar, that's the mean of the weights, plus minus the standard error of the mean, which was s over square root n in this case. So that would be the standard uncertainty when we use here the sample distribution. Because we had to do some measurements, this is also called a type B measurement. I hope I got this the right way wrong. No, this is type A. Sorry, this is type A. This is type B. I got it the wrong way around. So how do we actually combine these two measurements? The measurements of the resolution, the uncertainty of the resolution, and the uncertainty of our sample. So we can calculate the mean for our sample, and this would just simply be adding them all up and divide by 3, and if we do that we get the mean of 95.333 grams. We can also calculate the sample standard deviation. So here the standard deviation, and this is, I think, 3.511 grams. We can calculate the standard error, which we said is standard deviation divided by square root 3 in this case. For the standard error we get 2.028 grams. So we said this standard error is one component of the uncertainty, so that we could say this is U1, and we have got the other uncertainty U2 here, which comes from the resolution of the measurement. So we can basically say our mean for the average weight of the banana equals plus minus the combined uncertainty, plus minus combined uncertainty. And for this combined uncertainty, we know how this works. Combined uncertainty in this case would be the square root of U1 squared plus U2 squared. And we are currently just simply adding things up. Everything is added. So we would use the absolute uncertainties. We don't need to convert them into relative uncertainties. So what we would get here would be for the combined uncertainty equals square root of 2.028 squared plus 0.288 squared. So we can calculate that here. This gives us a value of 4.1957 for the combined uncertainty, or if we calculate that from the root, equals 2.0483 grams. So that's our combined uncertainty, where we combine the standard error for the sample uncertainty with the standard uncertainty from our device, from the uniform distribution. And what we see is that our uncertainty is pretty close to the uncertainty from our sample here, which means the sample uncertainty has the lion's share in the overall uncertainty, whereas the resolution uncertainty really doesn't play a massive role. So what we can do now is we can report our mean weight for a banana. That would be x bar plus minus the combined uncertainty, and that would be 95.333 gram plus minus 2.0483 gram. Now we need to be careful about the significant figures. We know that an uncertainty should be reported only to one significant figure, or two maximum. So we've got one significant figure here, and that is in the unit position. So we would report only to 2 grams. So we would report our mean weight as plus minus 2 grams, and we would adjust our measurement so that we have the same amount of decimal places. So we only have the unit position, so we would be 95 gram plus minus 2 grams. And this is basically how you calculate a combination of sample uncertainty with a resolution uncertainty. And of course the same thing would hold true if instead of a uniform resolution we would have a triangular resolution. Then just this value would change. It would not be 1 over square root 3. If it was triangular, it would be 1 over square root 6.